Hello guys, in this discussion section, we want to discuss how to do the two sample proportion test using chi-square test. Okay? So same data, let's say we have this two-way contingency table and we want to do the test related to the population proportions are the same for two groups. So let's say we have like true death rate of COVID-19, and we don't know what is this, but we're assuming that the death rate of COVID-19 in USA and Italy are the same. Okay, and alternative hypothesis is this P USA is not equal to P Italy, and we want to do this test using chi-square test. In the chi-square test, we need to calculate the expected number for each cell. Okay? So first, maybe you should draw this two-way contingency table based on the based on the types of the problem you have. Like some of the problem you will have in the exam will give you the two-way contingency table, and you can start it from there. But some of them actually didn't does not give you the contingency table, so you need to make sure you can make this two-way contingency table when you read the problem. Okay, so we are assuming you already draw this two-way contingency table, and the next step for the chi-square test is to calculate the expected number, okay, expected count. So what is expected count? So let's just talk a little bit about the two-way contingency table we have here. When we look at this column, will give you some information of true P. So what is the true P here? I mean, if you try to estimate the true P using this column, I would say P naught hat will be 58 divided by 159, because we have observed like 58,000 people who have been died from COVID-19, and our total observation number is 159,000. So I'd say if I want to estimate the P true death rate of the COVID-19, I would use this number. Okay, so this is the theoretical death rate of COVID-19, and the number of observation for USA was 95, right? So if this rate is the true rate, then I would expect that 95 multiplied by this P naught hat, which is 58 divided by 159. So this is, what does this mean? This is the expected number of people die from COVID-19. So, right? And if I want to calculate the expected number who will recover from the COVID-19, then I would do this 95 multiplied by, now since this one P not hat is the true death rate of the COVID-19, then recover rate is actually 1 minus P9, which can be calculated by 101, this one, right? The number of observation for people who has been recovered from the COVID-19 and divide by 159, which is the total observation number. So since we have, I need to put in USA here. Okay. Since we have 95,000 people in USA, we are expecting that this much people, like 95 multiplied by 108 divided by 159, which is the 1 minus P not hat, right? So we are expecting number of people who recover from COVID-19 in USA. Okay, so we can do the same thing for Italy, right? So let me just write it down. Two number quickly. So 64, we have 64 for this is death Italy, and 64 multiplied by 101, this is recover Italy. Okay, so this is the expected number, expected count for each cell. So if you calculate these four, and then for each cell, this number, let's just calculate what is the value. So 95, 58 divided by 159. So if I calculate this calculation, I got 34.65. So I will just write it down here, 34.65. Okay, so we can actually calculate the four numbers. I mean, for each cell we can calculate the expected count, and that number will be different from the real observation for each cell. So for example, for the first cell, we have observed 36 here, but our expected number is 34.65. okay, so once you calculate these four numbers, let me just pause, and then I will fill the every cells here. Okay, I have calculated the expected count for each cell. So I got these four numbers, and we can see that there is a difference between the actual observation and the expected number. Okay, so when you think about the meaning of this expected count, is that we are calculating these numbers only use the information we can get from the marginal distribution, which means we don't see each cell, we only use the information from this column and this row, right? This row and this column. Okay, if the country variable does not affect to the death rate of the COVID-19, and we are expecting these white number, actual observation, and the red numbers, expected count, will be really similar. I mean, become really similar. So if the difference between these two numbers are big, that could be a reason that we can reject the null hypothesis, which is the death rate of COVID-19 in USA and the death rate of COVID-19 in Italy is true. Okay? So chi-square statistic, usually write it down like this: chi squared, Greek letter chi and square, can be calculated by summation of expected number observation, subtract expected number, and then squared, divide by expected. So my first observation is 36 minus expected number is 34.65 squared, divided by 34.65 plus, what is the second one? We have 22 minus 23.34 squared, divided by 23.34 plus, we have 55, and our expected number is 60.34 squared, divided by same number, plus 40.65 squared, divided by 40.65. So if you calculate this, you will get if I calculate this, I will get 0.204117. Okay. So now I got the chi-square test statistic, and which is 0.204, and I know the chi-square test statistic can be parameterized with the degree of freedom. So we need to figure out what is the degree of freedom of this test statistic, which is 0.2041217. This degree of freedom can be obtained from the number of rows in the table and number of columns in the table. So we have two-way contingency table, which is 2 rows, which has 2 rows and 2 columns. And this degree of freedom can be calculated by number of rows minus 1 multiplied by number of columns we have in the table minus 1, so which is just 1. So degree of freedom 1, and we have test statistic value like 0.204. Okay. So if you look at the chi-square table in our textbook, the first row represents the degree of freedom 1, right? So this one, and this is the test statistic value, and the corresponding p-value is the column name. So if I have 1.64 with degree of freedom 1, then the p-value is 0.20. Okay. So then we have 0.204 as my test statistic. Then based on the table, my my test statistic is less than this one, right? And I know this value corresponding to 25%, 0.25 p-value. So let me just go back to my table, which means the chi-square distribution looks like this, and then I know that 1.32 corresponding to the p-value 0.25, and I know my test statistic is way smaller than 1.32, so this is the p-value that is corresponding to my test statistic, and I know this 1.32 corresponds to the 0.25. Then what I can say is my p-value is larger than 0.25, right? So if my alpha is 0.05, then my p-value is larger than this one, right? So since my p-value is larger than 0.05, I cannot reject the null hypothesis, okay? Which means if my contingency table looks like this, so 36, 22, 55, 59, 42, 101, 95, 64, 159. If my two-way contingency table looks like this, then I will get my chi-square test statistic as 0.20, and I know that degree of freedom is 1. So if I look at the chi-square table, then my p-value is way larger than the really large, so I cannot reject the null hypothesis. Okay. However, you guys will see if I using my real data, which is COVID-19 table, I will get I can reject the null hypothesis because my chi-square distribution will be chi-square test statistic will be really large. Okay. Okay, so we are going to do the two samples proportion test using chi-square test in SAS. So this is the code for loading the data, right? So we already have loaded our COVID-19 data before, but I will just submit again. So my SAS, in my SAS system, print data is equal to COVID-19. Let me just check. So I already have this data set, and to do the chi-square test is actually we are using the same frequent procedure, but with a different option. So I put the expected here and the chi-square option. So if I run that code, I'll get this table, which has the expected number in the table, right? The second number is expected number, and we have this table for the chi-square. So my chi-square statistic is 227, and we know that our degree of freedom will be 1, and corresponding p-value is 0.0001. Okay, and since our number of observation for each cell, these expected numbers are really large, so we don't need to use a Fisher's exact test, which is this one, right? So if our expected number for each cell, one of them at least, if we have one cell which has the expected number is less than 5, then you guys should look at the Fisher's exact test rather than the chi-square statistic. Okay, but in here, since our expected numbers are so big, so we don't need to look at the Fisher's exact test. We can just go with the chi-square. Okay, some of you may be confused that in my previous chi-square test statistic is really small, such as 0.204, but that's I intentionally did that because if we using that this table, like my numbers are not 36,000. I used this one here, like 3622, and my total observation is 159. If I using this table, I will get this test statistic. Okay, so this one. Okay, this 0.20412. But if I using the real data, which is like really big, then like this, really big, then my test statistic for chi-square will become really large. So my p-value also becomes so small, so that in our case, since my p-value is really small, I can reject the null hypothesis, which means the COVID-19 death rate of the COVID-19 in USA and in Italy will not the same. Okay, so we can reject the our null hypothesis based on our p-value.